Hello everyone, I'm Neeraj Kumar from CSC B6. Today we're gonna discuss about desktop topic, applied physics. The topic is the differential efficiency of quantum well lasers. The quantum well laser has by now a few well established properties at variance with those of the now well understood double heterostructure. It has extremely low threshold currents, well below those predicted by the simple extensions of DH laser theory. Temperature coefficient of the lasing threshold current to sometimes better, also sometimes worse than DH laser. High frequency modulation capabilities, low degradation rates, etc. It is therefore interested to understanding the physical basis leading to these operational characteristics, as they are intimately related to the two-dimensional nature of electron states in the structure. The purpose of this short review is to demonstrate that the operation of the QWL is strongly connected to these bidimensional characteristics, and that surely it is a good laboratory to understand the pros and cons of low dimensional devices. The extension of the QWL concept towards lower dimensionality will be briefly addressed at the end of this paper. The two main opposite effects in quantum well lasers. The number of available quantum states in the active region is strongly diminished. In the z-0 direction, that is perpendicular to the active layer plane, the thickness of the order of 200 amperes or less reduces the allowed values of momentum. In that direction, to one or a few quantized values within occupied states at threshold, that is z few kt above the ground state, whereas the number of occupied states is a 1000 ampere DS laser would amount to a few tens. Second point, the efficiency of the emitted photons to interact with an electron-hole pair to induce another stimulated recombination process is strongly reduced because of the poor optical confinement and has two origins. Firstly, a small confining material thickness. The wave-guiding properties of a DH are and usually confine optical wavelengths to a natural extension of one wavelength, the more so as the confining layer thickness diminishes. Secondly, the rather wide optical wave has an overlap with the active layer which diminishes as therefore both effects tend to diminish the optical confinement factor R as D2 within a approximation expression. The Bussard graph shows the differential efficiency of quantum well lasers. R is equal to d by lambda naught whole square into 2 pi whole square into n into delta n, where lambda naught is the wavelength in vacuum, n and delta n are the average and differences in indices of refraction of the materials of the ds. From the preceding discussions, it is clear that in single quantum well lasers, the diminution in R is the unacceptable unless a scheme is used. The other alternative, that is the use of native QWs, will be discussed later. Overall, one calculates that the decrease in number of states tends to balance the decrease of available quantum states to be inverted at threshold. The more subtle effects in 2D quantum well lasers. In order to analyze in more detail the operation of QWs, one has to consider the following effects. The Arquer 2D DOs led to several specific effects. Gain remains finite even for low hand filling in opposition with TH lasers where the DOs and therefore the gain tends to zero. This implies that the gain versus current curve is steeper than in 3D, and also that lower temperature operation of QWs will be excellent with threshold current reaching to very small values at extremely low temperature. The gas and gas case. Numerous laboratories have reported excellent results and gas and gas as single quantum lasers. Besides their low threshold current, which is understood in terms of the above-mentioned improvement factors. Several hitherto unexplained results only recently received complete explanation. The advantage of the green SCH structure over the SCH is due to their smaller dose in the light confining layer. In normal conditions, the detailed calculation of carrier densities at threshold yields a quasi-Fermi level which is quite high in the quantized layer than the typical 60 milli electron volts. On the other hand, optimal 2 is not Havett's associated with low threshold QW. Standard MQW laser have better 2 than DH, green SCH and SCH laser in decreasing order of merit. MQWs are the most two-dimensional lasers as the potential barrier of the confining material is the highest and therefore limits carrier leakage. In that case, the Fermi Dirac tail unuseful electron because uninverted is smaller constant dose than in 3D. Square root increases. SQW versus MQW laser operation. Seen from figure 3, gain appears at lower injected current in figure 3. The model gain variation as a function of injected current density for various numbers of quantum wells. Note the situation of the Z is equal to 1 quantum state for the single QW laser above X 100 ampere per centimeter square and the onset of N is equal to 2 quantum state transitions leading to higher gain of 300 AGC. Net gain starts at higher currents for increasing number of wells because of the increasing number of states to be inverted. Well, thickness is 100 amperes from Arakawa and Yariv SQW than in MQW due to the smaller dose to be inverted in former case. The gain as INP and gain as TNIAI as QW laser. In strong contrast with the material system, no laser emission could be obtained in SQW lasers in the gain as materials case. The situation arising is clearly shown in figure 5 and in measured gain curves as carrier injection heating of the carrier occurs presumably by Auger effect. It decreases the carrier inversion that is the gain and increases dramatically the confining layer population. The structure shown in figure 5. Additional properties of QW lasers. Besides their good current threshold and two QW lasers possess a number of additional important features which make them highly useful. 7.1 modulation limits. Due to the high differential gain DG/DZ of QWs where LIS, the injected current, Arakawa and Yariv have shown that an increase in speed response factor 2 times could be expected from QW lasers over DH lasers. This was confirmed by Uomi et al. Spectral line width from the same high differential gain in QW lasers. Arakawa and Yariv S,220 have predicted narrower line width than in 3D DH lasers. Although this improvement has not yet been directly measured, the related line width enhancement factor 51 is diminished by 50% in QW lasers as compared to DH lasers. The readability issues. Although relatively few degradation studies have been reported, figure 4 measure net optical gain curves and corresponding calculated curves for model gain. The low energy side of the gain curve is not treated in the theory as no band tailing is included. The high energy slope of the gain curve is well presented by the calculations. Impurity-induced interdiffusion. Impurity-induced interdiffusion of quantum wells has been evidenced in many material systems with various N and P-type implanted species. It allows to transform implanted region with thin wells and barriers into an alloy with the average composition. The alloy has the usual properties of light and carrier confinement. Therefore, one can use such as effect to construct a variety of strip geometry lasers, window lasers, that is, lasers where the active region does not extend to the external fa- facets, etc. Excellent results have been obtained by such techniques which permits to manufacture complex devices with simple planar type operations while one would otherwise require multiple steps and deposition processes. Evaluation towards 1 and 0. The importance of fluctuations. It is by now quite well established that interface disorder is limiting recombination line sharpness in quantum wells, although some recent interrupted growth experiments evidence excellent improvement. However, at the expense of high impurity incorporation, the required high density of state, that is, high number of 1 and 0D systems, as is evident from the new discussions of the 2D QW. One cannot diminish too much to material volume for two reasons. First, required carrier densities per 1 or 0 will are so high that total band filling would occur before enough gain would be obtained. Secondly, the confinement factor would be vanishingly small. This is end of our presentation. I hope you gain some knowledge regarding differential efficiency of quantum well lasers. Thank you.